Hello, dear students and teachers. Previously, on our discussion, we have tried to revise some of the main points on thermodynamics. We have tried to list out and try to explain about the second law of thermodynamics. We are able to state different statements of thermodynamics. We have said that no heat engine can perform as efficient as that of the Carnot heat engine. We have also tried to see that no process is possible for a heat to flow from colder body to hotter body. No process is possible for an overall decrease in the entropy of the universe. As well, we have said that no heat engine can completely convert heat energy into mechanical work. This was what we have previously stated. And today we'll try to see about the second unit, which is oscillations and waves. So we should have to classify these two. First, we'll try to see about oscillatory motion, then we'll try to see about waves. Unit 2 says that oscillatory motion and waves. So first, what does it mean by oscillatory motion? Oscillatory motion is a type of motion in which a given oscillator or a given object is moving towards and forwards, backward and forward, so that it is known to be a to and fro movement of particles. We have different examples associated with oscillatory motion, but the most common are a mass spring system and simple pendulum. We are going to discuss about these two. Under this concept, we have basic terms under oscillatory motion. And these terms are like cycle, period, frequency, amplitude, and so on. Cycle means for a given oscillator, here we can have a mass, for a given oscillator, the complete path, one single complete path is known to be cycle. Okay, cycle means complete trip of oscillator. For example, here we have a pendulum. If I release it from here, it might swing there and back here, so that one complete trip is known to be cycle. And period is the time required for one complete cycle. It's the time required for one complete cycle. Frequency is always measures the number of recurrence or the number of redundancy. So it says that frequency is the measure of complete oscillations per a given time t. Okay, so it is the inverse of period. It's possible to have 1/2 is a unit of frequency known to be hertz. And the other thing is here, equilibrium position. For a given oscillator, equilibrium position is the initial position of the oscillator before force is exerted on it. Amplitude is the maximum possible displacement from the oscillator. For example, here you have oscillator. This is the equilibrium position, x equals to 0. As this object tends to move here with a maximum possible elongation and move back here, a maximum possible compression is known to be amplitude. Here it might be a positive amplitude or a negative amplitude. It's also possible to have amplitude for swinging pendulum. Here you do have the maximum positive amplitude or the maximum negative amplitude. This is the maximum possible displacement from equilibrium position. Restoring force is a force which is exerted always towards equilibrium position. It's a force which is always acting towards the equilibrium position. For example, if I try to pull this bob, we call it bob, in this direction, there is a force which tends towards the equilibrium position. And that is what we call restoring force. If I try to pull this one, the spring tends towards the equilibrium position. Or if I try to compress the spring tends to push backward to equilibrium position. A restoring force is a force which is always acting towards the equilibrium position. And simple harmonic motion is ideal motion in which that the oscillator keeps its amplitude always free from dissipating energy. That means for the oscillators here, if you have a maximum possible amplitude, so that this mass spring system always keeps its amplitude constant or the energy remains constant. There is no energy loss. Suppose if I pull the pendulum and release it, the energy in SHM, in simple harmonic motion, the energy remains constant so that it swings forever. That is what simple harmonic motion means. Sinusoidal function is a function or mathematical expression used to represent waves or sinusoid or oscillatory bodies. Oscillatory bodies might be represented using a sinusoidal function, meaning you can use sine or cos. trigonometric functions able to represent the position of those particles. For example, here it's possible to use the position using a cos omega t or theta, or using a sine omega t. Mathematically, it's possible to use or express the displacement of oscillatory body using x as a function of time t, a sine theta. Well, theta, from angular displacement, we know that angular velocity or angular frequency is angular displacement over time t. From this, you can find that theta is equals to omega times t. So, the displacement as a function of time t in oscillatory body can be expressed using sine or cosine. The difference is that when you use sine function, the oscillator starts to oscillate from equilibrium position. When you use cosine, oscillator starts to oscillate from the maximum compression or elongation. This is what it says. And its amplitude remains constant. Since the motion is oscillatory motion, keeping the amplitude constant, the energy constant. And it's possible to determine the velocity of the oscillator. Because that the displacement is expressed in time t, it's possible to derivate and find the velocity. We know that velocity is the first derivative of displacement, dx by dt. We have two displacement functions, a sine omega t and a cos omega t. When you are trying to derive this, you can find a velocity expression as omega a cos omega t, or the negative of omega a sine omega t. Again, when it is cos, it starts from the amplitude. It might be from positive or negative amplitude. Here it says positive, so it starts from positive amplitude. When it says sine, it starts from equilibrium position, but in front of it, you have a negative omega a. And that negative tells you that it's moving or tending to move downward, like this. Okay? Starting from equilibrium, it's moving downward. This is the negative of omega a sine omega t. And every quantities in front of sine or cosine function tells us the maximum value of this quantity. In this case, omega times a is known to be the maximum velocity. The maximum velocity. And previously, here it says a. A means the maximum possible displacement, or the maximum possible displacement is known to be amplitude. Call it to be amplitude. Again, it's possible to find the acceleration of the oscillatory body by derivating the velocity with respect to time t. So when you derivate, you can find the acceleration as the negative of omega squared a sine omega t. When you derivate this, you can find this. The negative of omega squared a cos omega t. Again, every quantity before sine and cos tells us about the maximum value of this one. And this value is actually this quantity's acceleration. And the negative of omega squared a, or plus or minus omega squared a, is the maximum acceleration. Okay, the maximum acceleration. And when it is sine, it means it starts from equilibrium position. When it means by cos, it starts from amplitude. And the amplitude might be negative or positive. For example, the negative of squared a sine omega t can be represented like this. Since it is sine, you should have to start from equilibrium position. But it says the negative, meaning you are moving downward. And the negative of omega squared cos, since it says cos, you should have to start from amplitude. From which amplitude? It says the negative one. So you should have to start from this one and so on. It's possible to have velocity, displacement, and acceleration of oscillatory body. It's possible to use such an expression. Summarized it. If x is expressed as a sine omega t, its velocity can be determined as, or if you derivate it, you can find it omega a cos omega t. Furthermore, if you derivate it into acceleration, you can find it to be the negative of omega squared a sine omega t. Here, x as a function of t, a cos omega t might be derived and find the velocity as the negative of omega a sine omega t, and derivate it, you can find it to be the negative of omega squared a cos omega t. Now, you can find a good relation between acceleration and displacement, because that it says a sine omega t, and a sine omega t is displacement. For this as well, a cos omega t means x. Therefore, the negative of omega squared, instead of a sine omega t or a cos omega t, you can substitute with x. So here you'd have a relation between acceleration and displacement. What kind of relation? They do have a direct relation between acceleration and displacement, but it says negative, meaning they do have a direct proportionality in magnitude but opposite in direction. Acceleration and displacement in oscillatory motion has a direct proportionality in magnitude but opposite in direction. Keep this in your mind. And it's also possible to find a relation between velocity and displacement. How? It's possible to use x sine omega t, the previous one. If you derivate it, you can find it to be omega a sine omega t. To make it similar, you can multiply both sides by omega and squaring it, both sides, and adding it together, you can find such an expression. Okay, adding this, you have such an expression. And this expression tells us that velocity of oscillatory body and displacement. And this one is amplitude. Omega is actually angular frequency. Therefore, at x equals to 0, as x equals to 0, meaning at equilibrium position, the velocity becomes maximum, because if it is 0, we can find it to be omega a. And omega a is known to be the maximum velocity. So as oscillators tending to move and reach at equilibrium position, it has a maximum velocity, but it has 0 acceleration. The displacement is 0, the acceleration is 0, but the velocity is maximum. Whereas at x equals to plus or minus amplitude, the velocity is 0, because at x equals to amplitude, amplitude squared minus amplitude squared gives us 0. This is what it says. So you should have to find a relation and you should have to recall these concepts. Now let's try to determine period in simple harmonic motion. For oscillatory bodies like mass spring system and simple pendulum in oscillatory motion, it's possible to determine their period. Okay? The period can be determined from the above relation, and for mass spring system you can have such equations. It says that period T, capital T, is period 2 pi square root of mass m over k, which is the mass, the stiffness of the spring, or force constant of the spring. So here you have mass and the spring with k. The period T is equals to 2 pi square root of m over k. This is how we relate. And for simple pendulum, it's possible to determine the period as period T is equals to 2 pi square root of L, the length of the thread, over G. So here you have a pendulum. The pendulum of length is L. Okay? It is independent of the mass of the bob. Actually, the mass of the bob increased or decreased, the period does not affect for a given angle theta. Okay? Keep that in your mind. But for mass spring system, the period depends on the mass of the object attached to the spring. Keep that in your mind. So generally, period for mass spring system can be determined as m over k, 2 pi root of m over k. You can find the frequency inversing this one. Frequency is the inverse of period, so that 1 over 2 pi root of k over m is frequency. And the period for a simple pendulum is 2 pi root of L over G. If you want to find the frequency is inverse of period, you can inverse this and find the frequency as 1 over 2 pi root of G over L. Energy in simple harmonic motion. Let's try to see energy in simple harmonic motion. We can take a mass spring system or a simple pendulum as well. For example, here we have a mass spring system. As this mass spring system in SHM oscillates here and there, sometimes it has a maximum possible potential energy, like on the amplitude here and there, we have a maximum potential energy. And then, since the velocity is 0, we have 0 kinetic energy, 0 kinetic energy at the amplitude. But we have a maximum possible potential energy. Then we released it, it has its own velocity, there is a kinetic energy. As well as there is displacement, there is a potential, elastic potential energy. The sum total of these two is always constant. Okay? For a simple harmonic motion, for SHM, the total energy, the sum total of kinetic energy and elastic energy is always remains constant. And it's given as energy is equals to 1 over 2 k a squared, and energy is associated or related with that of square of the amplitude. For a given oscillator, we have the amplitude, and energy is associated with that of the square of the amplitude. This is what it says. There is also different types of oscillatory motion. So far we have been trying to see simple harmonic motion. We have also damping oscillation. Actually, simple harmonic motion is ideal motion in which there is no energy loss. Suppose if you have a pendulum here, it swings here and there, it's colliding with the air particles, gradually it's losing its energy, and at last it stops. Such a motion is known to be damping oscillation. Damping oscillation, the given oscillator oscillates and gradually decreases and loses its energy so that it stops. Why it stops? Because there is a damping force. And the damping force of the medium is related as the damping force of a given medium is related with that of the velocity of the oscillator, but oppositely. Okay? As the object is tending to move here in this direction, the oscillator, the damping force is opposite to that of the other side. For example, as this oscillator is tending to move downward, the damping force is acting upward like a frictional force. Okay? As this object is moving upward, there is a downward damping force. Damping force is related like this, and you have equation known to be the damping force is equal to the negative of B times V, where B is known to be damping coefficient of the medium. Actually, for different medium, we have different equations. And one thing important here, the amplitude of a damping oscillator gradually decreases. For example, initially, the amplitude here is maximum, and then decrease, and then at last it decays. So the amplitude of damping oscillator decays exponentially. Gradually, as time goes to infinity, its amplitude becomes zero, or it will stop oscillating. Such a motion is known to be damping oscillation. Damping oscillation might be classified as underdamping, critical damping, and overdamping, and so on. You can find that on your textbooks. Here we have resonance, a so-called resonance. Resonance is a phenomenon, which is sometimes a disastrous phenomenon, which says that when the natural frequency of a given oscillator is the same as that of external driving frequency, the object tends to have a maximum possible oscillation. Even it breaks the bond which correlates or tries to relate or catch the objects. Therefore, suppose here you have one of a good example is Tacoma Bridge. There is in your textbook. The Tacoma Bridge is moving here and there with its own natural frequency, but suddenly the wind is there. The driving frequency of the wind is equals to that of the natural frequency of the oscillating bridge, the Tacoma Bridge. So that as the driving frequency is equals to the natural frequency of a given oscillator, that is very difficult, meaning that the object is going to have the maximum possible amplitude. When it vibrates, it has a maximum possible amplitude so that it may break its bond. In this case, if you see a glass on a speaker, if you give a speaker's frequency is the same as that of the natural frequency of the glass, soon after it's going to be shattered, meaning the driving frequency of the speaker and the natural frequency of the glass remains constant. For that, the particle of the glass is going to have the maximum possible amplitude. That's why it's going to be shattered. Such a phenomenon is known to be resonance. So far we have tried to see about oscillatory motion. Now let's try to see about waves. What does it mean by waves? Well, waves are energy carriers. Suppose if you propagate or something, if you release energy, that energy might transmit it through a given medium. Suppose here I'm trying to tell you something and it's propagating through air. For audience, some here, but it might be propagated through electromagnetic waves. Or it's possible to have a water ripple here. If you drop a stone or something, at some point, there will be a disturbance. And that disturbed particles are going to disturb the other particles, so that they are going to transmit the energy all along the surface. Such a means of energy transfer is known to be waves. Waves are energy carriers. Okay? They transmit energy through a given disturbed particle. There are different types of waves, actually depending on medium. We can have mechanical and electromagnetic waves. Mechanical waves necessarily needs mechanical medium for their propagation. Electromagnetic waves are waves which can propagate through vacuum as well as through medium. The good example of mechanical waves are sound waves. A good example of electromagnetic waves are microwaves, radio waves, and so on. They can propagate through vacuum, they can propagate through medium. Okay. Then the other category of waves is transverse waves and longitudinal waves. Transverse waves, this is depending on the orientation, meaning the disturbed particles has a perpendicular orientation with that of the direction of the wave. For example, here you have a tensioned string. You just produce a wave here, you just disturb. The particle here, P, call it P, the particle is moving upward and downward, whereas the wave is moving to the left. So as the wave moving to the left, in this case to the right, the particle is tending to upward and downward. So the wave direction and the particle direction are mutually perpendicular. So such a wave is known to be transverse wave. Okay? Whereas longitudinal waves are waves which has the particle is parallel to that of the direction of the wave. For example, here you have helical coil. Okay? Or as this coil is moving like this, it's possible to have compression and rarefaction, and the particles tend to move like this. It's moving here and there. The wave is moving like this. So the wave and the particle has a parallel orientation. Such a wave is known to be longitudinal wave. A good example of longitudinal wave is sound wave. Sound wave has parallel direction with disturbed particles, whereas transverse wave has like tension string, water ripples. Electromagnetic wave itself is a transverse wave. Here we have common terms used for waves. As we have used in oscillatory motion, we have cycle, period, frequency, amplitude, restoring force, simple harmonic motion, and so on. These are the basic terms that we have seen in oscillatory motion. But under here, we have also basic terms like period, frequency, and wavelengths as well. What do you mean by wavelengths here? Wavelengths means for two successive waves, we have correspondent points. Suppose here you have this wave. Let's take this one. From this to this is one wave. From this to this is another wave. Okay. Here the peak points of the waves is known to be crest. We call it to be crest or peak value. And there are points in which they are moving downward. For example, you might take the surface of the water. There are upper points and downward points. Okay, there are up and down points. The upper points are known to be crest or peak. The points which are found deep there is known to be trough. We call it to be trough. Or you might have a tensioned string so that it's moving up and down. The upper point is known to be crest. The lower point is known to be trough. So if you have two successive waves, like here, the red one and the white one, the distance from crest to crest, or the distance from trough to trough, or any other corresponding point is known to be wavelengths. So wavelengths is the distance between correspondent point of two successive waves. This is what we call wavelengths and symbolized by Greek letter lambda. Period is the time required for one complete oscillation in oscillatory motion, but here it is the time required for one wave to be completely passing a given point of observation. For example, we are trying to observe this wave. Let's say that this is point of observation. So as this wave propagating to the right, you just start to observe here, so that it might completely passing the given point of observation. So the time it took for a given wave to completely passing is known to be period. And frequency is always it measures recurrence or redundancy of something. Suppose you are observing waves passing a given point and try to count the number of waves. So as you count, one wave is passing, you are going to count. So you are going to record the number of waves passing that single point per a unit time t. So frequency is the number of complete waves passing a given point of observation per a time t. This is what we call, suppose here 15 waves are passing a given point within 3 seconds. So what is the frequency? Well, the frequency says that 15 waves are passing a given point within 3 seconds. So that within 1 second it's possible to have 5 waves. This is what it says. If you are going to determine the period, you should have to inverse the frequency. So the inverse of this frequency gives us 1/5, which is 0.2 2 seconds. For every 0.2 seconds, one wave is completely passing. It's possible to have that. And the other point is the speed. So far we have seen wavelengths, lambda, period t, frequency, and now let's try to see about the speed of a wave. Speed is generally given to be displacement over time t, okay, or distance over time t. The distance it took for one wave to be completely passing is known to be wavelengths, and the time it took for one complete wave is known to be period. So lambda over period is known to be, or 1 over period is known to be frequency. Therefore, it's possible to have wave speed as lambda times frequency. Okay. So dear students, so far we have tried to see about the concept of oscillatory motion as well as wave. We have defined basic terms that are going to be used under waves. Next time we are going to see the mathematical expression of waves. So see you then. Bye bye.